Daniel Ochoa, is that correct?
Yes, that's correct.
Okay. Please go ahead.
Okay, thank you for the introduction. Yeah, I'm Daniel Ochoa. I'm a PhD student at the University of Colorado in Boulder. And today I'll be presented the work titled Computation-Aware Distributed Optimization of Our Networks, a Hyperdynamical Systems Approach. And this is joint work with Professor Jorge Poveda from the University of Colorado in Boulder and Professor Cesar Uribe at Rice University in Texas. So in this work, we're mainly motivated by cyber-physical multi-agent systems, but not only by the general sense multi-agent systems, but multi-agent systems in which each one of the agents inside of the system is going to have some kind of computational power that we're going to care about for the design of our algorithms. So these kinds of systems appear all the way from power systems and power distribution to control flow of vehicles in transportation systems in which we can have some interaction between autonomous vehicles and smart traffic lights, but also appear in water distribution systems and in the usual network control problems. So in these kinds of settings, we are mostly interested in maybe making some interesting signals of our dynamical system to get to some desired operating point. And in doing so, it is usually an interaction between an optimization problem and some control algorithm that desires to achieve this convergence to desired point of operation. And although during the last decades, a lot of different algorithms have appeared in order to solve this kind of problems, it is often assumed that these computational constraints that each one of the agents inside of the system have can be neglected. So in some sense, for the simplicity of the analysis, we can assume that, for example, if you are computing some kind of rating for your system and for your optimization dynamics, that you can actually access it in instantaneous times. So what we like to do and what we did for this work is to actually try to consider this computational constraint inside of the design of our optimization problem for a network. So under this setup, we specifically consider the consensus optimization problem, in which we try to model the interaction of these agents inside of the cyber-physical multi-agent system as a graph of interconnected agents. And you can think of each one of the nodes inside of the graph as these agents that have some kind of computational power. To each one of the agents, we also endow them with a local cost function. And the objective of the whole optimization problem that we would like to solve is to find the overall network state Z that is going to minimize the sum of the local cost functions. And it's of utmost importance that when we're doing this minimization problem, we also respect the sparsity of the underlying communication network. So the agents are going to be exchanging information, and whenever we're going to design this kind of algorithms in a distributed manner, we'd like to respect the sparsity of the matrix L that is in the slide, and in which some sense abstracts what are the communication constraints between agents when they are exchanging information. All right, so under these settings, we'd like to have algorithms that have fast rate for convergence, because in a practical implementation, we definitely don't want algorithms that are too slow, but we also want to do so while still keeping robustness properties for our algorithms. And with both of these properties, we also like to keep the distribution as one of the main characters in our solution. All right. So for the fast surface of convergence, we take inspiration in the Nesterov-Soddy, which is shown in the slide, which is the continuous time counterpart that has been studied during the last 5 or almost 6 years of the super popular Nesterov algorithm that is used for acceleration in machine learning, for instance. I'm showing here one of the state space realizations that allows us for a easier treatment of the Lyapunov functions and for establish some stability properties for our algorithms. So X is going to be the main variable of the optimization problem, and Y is going to be this auxiliary variable that allows us to model the dynamic momentum. So one of the important things about this Nesterov algorithm is that we're multiplying by a dynamic coefficient the momentum dynamics of the system. And this allows us to have this nice acceleration property, which that can be shown to be actually optimal for all the different algorithms that optimization algorithms that only use gradient information in order to reach the optimal set. And whenever we will see this 1/t² convergence in terms of the cost functions, we're going to talk about this acceleration property. So it's really interesting to have this OD in terms of like for the analysis of different algorithms from the control theory perspective, because the continuous times allows us to leverage some Lyapunov techniques analysis that are pre-existent in the literature. But although this is really interesting to have this property, it has also really been shown that this the dynamic coefficient that is multiplying the momentum is actually a little bit problematic, because if you only implement the ODE as it is and you let this timer variable grow unbounded, you can actually design the disturbances that arbitrarily small and thus can be not identified by common sensors, and you can actually make the system unstable. So here in the slide, what I'm showing is that we applied and we designed this super small disturbance on the gradient, and we can actually make the y variable of the steady state representation grow unbounded, which is kind of problematic for safety critical applications or for the application in some cyber-physical systems in which lives can be involved. Right, so we'd like to apply some kind of nested of inspired algorithm, but try to fix this kind of robustness property and robustness issue. And it has been shown at first heuristically, and then it has been formalized in the literature, that one clever way of solving this issue is precisely not letting the timer variable to grow unbounded. So there is some kind of reset going on there in order to fix this robustness property. And we also have to do this in a fully distributed way. So again, the timer is one of the main challenges for us, because if we want to achieve the acceleration property, then we'll need only one timer for the whole network. At some point, we'll need this timer to be like the information of the timer to be the same for each one of the different agents. But in order to do this in a distributed way, we'll need to have different timers for each one of the agents. And we'll like to implement some kind of synchronization algorithm so that in hopefully finite time, we achieve the synchronization of the different timers, and that the timer variable behaves as one for the whole network. And the other thing that was also important is that we need to maintain the sparsity of the communication matrix of the graph in order to be compliant with the communication restrictions that the cyber-physical system has. Okay, so here I'm just showing some of the works in the literature that have been somehow related to these different problems, but up until now they haven't been jointly solved together. So our approach was precisely to do this, to leverage the tools of hybrid dynamical systems. First of all, because we need to somehow reset this timer variable in order to recover robustness properties for our algorithm. So we are going to have in some sense, some discrete time evolution. So we have some jumps that are described by this jump map G, and that happen whenever the state of our system belongs to the jump set. And we also have the nature of dynamics or the flow dynamics that are going to make the optimization and accelerate the optimization of our problem. So that's why we leverage the properties of hybrid dynamical system. And most importantly, what we would like to do is to study this property, this notion that's called the uniform global asymptotic stability. So actually what happens with the nested algorithm is that it is not uniform under all the different initial conditions because of this timer that is growing unbounded. So by resetting the state, we can actually find a Lyapunov function that, and in turn, a class kappa L function beta that is going to characterize this notion of uniform global asymptotic stability, which means that you can always bound every possible solution for your dynamical system H by this class kappa L beta function. So this is just a way of characterizing the notion of uniform global asymptotic stability. Moreover, we are more interested in designing algorithms that are well posed. Why are we interested in this? Because whenever you design this algorithm, then for free, almost, you get robustness properties. I'm going just to go a little bit into detail of what robustness means for us in this sense. But first, because we want to design well-posed hybridynamical system, these are one of the way of actually having sufficient conditions for achieving a well-posed hybridynamical system. So you will need that your both flow and jump set are closed. F and G, the jump and the flow map, are outer semi-continuous. F and G are locally bounded, and F is convex positive. So whenever we're trying to design this kind of algorithms, we look into these hybrid basic conditions, and if we can achieve them, then we naturally and are sufficient conditions to achieve this well-posedness. In turn, if we can prove some kind of UGAS uniform global asymptotic property for a desired set, which in this case of optimization algorithm will be the optimal set of the cost function, then when the system is perturbed or is disturbed by some kind of disturbance in the states or in the maps or in the set, then we cannot guarantee actually this property of robustness, which is going to be called the semi-global practical asymptotic stability, and SGPAS for short. So what this says is that basically for every set of initial conditions and for every given precision node that you want away from your desired set, which for us is going to be the optimal set, then you can actually characterize an upper bound for the different disturbances that you can apply to your system, so that all the trajectories that I start from this compact set of initial conditions are going to arrive to this new or this precision inflation of your optimal set. So in some sense, like this is characterizing this SGPAS property is characterizing the robustness property under some given disturbances that are bounded from above. So well-posed hydrodynamical systems and UGAS of the nominal set of optimal values of your cost function is going to give you naturally robustness under disturbances. All right, so that's one of the tools that we use in order to bridge the gap between fast convergence properties and robustness. And now we want to also do all of this in a distributed manner. But before that, we tackle the optimization problem actually from the dual domain in order to get rid, in some sense, of this constraint that sometimes can be prohibitive in order to apply these momentum-based optimization algorithms. And the takeaway from this is that in this dual domain, and for this consensus optimization problem, everything and all of the different components of the gradient, or what is playing the gradient in our algorithm, can be actually computed locally. So that's really good for us in terms of the distributed optimization of the algorithm. So this is basically our two tools that we used, but on top of that, we made additional assumptions. So we assume that the local cost functions are continuous and strongly convex, that the communication graph is undirected, connected, and the time invariant. This is going to be useful for us in order to characterize that we have actually fixed time convergence of the timer variables of our system, and also that the level set of the dual function with domain restricted to this set are bounded. And this basically translates to the fact that you have a dual function that is radial unbounded, and this allows us to get the global part of our results. All right, so these are our dynamics. We call them hybrid accelerated restarting distributed dynamics, where we have an X, which is the dual variable, Y, which allows us to describe the momentum dynamics, and we have the different times that I have been talking about up until now. And we formulate this flow map that it's closely inspired by Nestor dynamics, but which we have to modify the gradient information, because precisely we cannot guarantee that at the beginning of our solution for the hydrodynamical system, all the different timers are behaving as one. So this does not actually commute all the time. So we had to put this, and this actually appears naturally when we're doing the Lyapunov analysis, this modification to the gradient. So it's closely related to the Nestor algorithm, but it's not trivial to get to this modification. You need to work it out a little better. All right. And we're allowing this to happen, all of the different flows, whenever the timer variables are between a small value TR and a bigger variable TR plus delta T. We allow the dual variable to be in RNP for multi-variable optimization problems. And here is the like feasible set of interest that we need to have. But the important part here is that precisely we're using the flows, and we're just allowing the flows whenever our timer variable that are bounded in or are evolving in a bounded set, and we let them jump whenever they arrive to an upper value. Whenever one of the timers arrives to an upper value, then we reset it and we communicate that information to the neighbors, and the neighbors in turn are going to reset themselves. And because the graph is fully connected and is undirected, then this synchronization and all of the timers are eventually going to have the same value at some point. And the jump, we can also reset the momentum state, the dual variable state to the value of the momentum state, depending on some conditions of the cost function. And which these pair of variables belong to some outer semi-continuous map, outer semi-continuous closures of some map. And this is everything done in order to satisfy the well-posed hydrodynamical system solutions. Okay, so this is basically our algorithm, and again we're jumping whenever we arrive to this upper value for our timers. Okay, so these are the dynamics, and we can actually prove that these are well-posed hydrodynamical system. And the main theorem for these dynamics that we propose is that under suitable conditions on the tunable parameters of the dynamics, And specifically, one of those is that we have to reset sufficiently slow, so we cannot reset sufficiently fast, but too fast in order to keep the acceleration properties. The set of minimizers of the cost function is UGAS. And for each compact set of initial conditions, if the reset policy is equal to 1, we can actually guarantee this exponential convergence to the optimal set of minimizers of the cost function. And if the primal is not Lipschitz and we have a resetting, a reset policy that's Q equal to 0, which conditioned what we did during the jumps with the dual variable, then we can have this convergence to the optimal set, which is actually an accelerated property in the dual domain, but whenever we come back to the primal domain, it becomes this bound. All right. So basically what we have done with this is that we have formulated an algorithm that precisely bridges the gap between these three things. We were respecting the sparsity of the graph because we modified the gradient, as I talked about in a few slides before. It is robust because it is well posed hybrid dynamical system, and we can guarantee UGAS properties, and the fast rate of convergence comes directly inherited from the Spark-Nesterov algorithm. All right, and how's the sketch of this proof? We basically use the reduction principle for hybrid dynamical systems in order to first prove that the synchronization happens in finite time, and after that we can analyze the convergence to this feasible set, and then the convergence to the optimal set, while assuming that the timer of the whole network acts as one. All right, and by doing so, we can actually compare this with the usual distributed gradient descent, and if all of the timers start synchronized, we can outperform that. But if they don't start synchronized, after some time has elapsed, then they synchronize, and we can actually outperform the usual distributed gradient descent. One important getaway of this is that if you implement resetting individually, and there is not coordination and sharing information of the resetting of the timers in your network, you can actually get disastrous results, which you are actually losing all of the convergence properties of your system. And the other stuff that we have to take into account is that, okay, you maybe don't want to restart this timer, but as we have said, if you don't restart this timer, then you can lose your convergence properties under the application of a sufficiently small disturbance. All right, so now with all of this, we're assuming that in order to implement these dynamics, the computation of the gradient happened like almost instantly. These were the different local components that were used in order to compute the gradient in the dual domain. But what happens if we actually consider it? If we consider that the computational constraints are there? So in order to do this, we interconnected the hard dynamics that we just proposed, that are well posed, with a dual first order oracle, in which we assume that this is a black box that has some dynamics and that has the ability to converge to some epsilon convergence that's closest to the actual value of the gradient. And we switch between both dynamics with this alpha variable that's a Boolean, a vector of Booleans that can get synchronized after some time, also with the same logic of the timers. And then after some time can act as only having one alpha. So then we can freeze the hard dynamics while we're waiting for the information of the gradient. So whenever we have alphas equals to 0, we stop the hard dynamics and we let the dual first order oracles to evolve so that they can converge to a neighborhood of the actual gradient values of the local components of the gradient. And whenever we switch it back, then we allow the hard dynamics to evolve. So the question here is, okay, we're allowing the hard dynamics to evolve with some sample value of the gradient, right? So that can be problematic. We might be allowing it to flow too much with wrong information. So actually, the world post-hybridynamical system property that we have here comes to the rescue, because what we can actually do is that given a precision in terms of how close you want to be to your solution of the whole optimization problem, then because you have this SPGA-AS property for your robustness, that you can characterize this margin of robustness epsilon star such that you can characterize how far or how wrong your information of the gradient can be before you ask again to the dual first order oracles. And with this characterization and having that you can only allow this flow to happen for some time t, then you can compose this sample data system in which we have the plant, the precision dynamics taking the place of the plant, and the dual first order oracles taking the usual place of the controller, to guarantee that the interconnection is actually achieves this semi-global practical asymptotic stability results to the set of minimizers. So basically what we have is that because we have UGAS and we have that the system is well posed, and thus there exists a class K-pile beta function, then we can characterize this margin of robustness, and in turn we can characterize this periodic sampling time at which we want to ask for some information of the gradient. And if the system is UGAS, which is that we have an actual functional exponential form for the beta function, then we can have actually this margin of robustness characterized in a functional form, and in turn have an actual value for this sampling time. So the getaway here is that if we have UGAS, we guarantee that you need to sample sufficiently fast, but not sufficiently, and you also need to do it sufficiently slow in order to keep the acceleration properties. And if that you have UGAS, we can give you a value at which you will need to sample information from the gradient. Right. So the main conclusion is that implementation of momentum-based optimization algorithms in multi-agent systems is not trivial. As we have seen, we're starting without coordination can be disastrous in order to keep like this dynamic momentum coefficient bounded. That the formulation in algorithms in terms of well-posed hyperdynamical system really simplifies their analysis and their fundamental limitations in hardware infrastructure. Basically, what we did was that we could include this hardware limitation because we had this well-posedness, and that the dual approach for the treatment of the optimization problem unlocks the possibility of treating the optimization problems in constrained settings and makes it easier to add momentum to these optimization algorithms. Our current research directions are focused on extending these algorithms to include additional dynamics to each one of the agents in the system, and also to include dynamics in how in maybe changing the connection of the graph sufficiently slow with time. That's all for today. Thanks.
Okay, thank you for the talk. It's a very interesting talk. We do have a couple of minutes for a few questions. So please go ahead. If anybody has any questions. Any questions for the speaker?
I guess I have one. By the way, Daniel, very nice talk, very interesting. I guess being familiar with the hardware basic conditions, what do you use them for in your analysis?
So basically, in order to guarantee the synchronization, the map that we implement for the timer reset has to be the outer semi-continuous whole of some individual map that is implemented for the local agents. So that guarantees that our jump map is actually outer semi-continuous, which is part of one of the hyperbasic conditions. Also, we need the set to be closed for each one of the timers. So that's why we include both of the ends in the flow map, in the flow set and in the jump set. So both of them are closed. And the continuity comes from the fact that the OD, the Nesterov OD is continuous whenever this T value is greater than 0 in the dynamic coefficients. So yeah, it's basically we use it in the jump map. It's like the one that which it appears the most, and we had to more work than what was already done in order to guarantee that the map was utterly continuous, and thus that the hyperdynamical system is well posed.
Right, I understand that, but again, what kind of theoretical result you're using that requires the well postedness? I wasn't able to.
Okay. Because you have the well postedness and we have the UGAS property for the properties of the well postedness allows us to have these robustness properties, which in turn, in terms of considering the hardware limitations, these robustness properties are translated in the fact that we can consider errors in our gradient in some sense, that these can be these disturbances for our system, and that we do not actually need to have all the information of the gradient at all times. So we use that well-postness in order to have the robustness properties for our algorithm, which in turn allows us to evolve without the full information of the gradient at all times.
Right, but do you need compactness of the asymptotically stable set?
Yeah.
Do you have a compactness assumption, or?
Yeah, because we assume that the level cells of the dual cost function were always bounded, and because of the form of the cost function, because of the assumption of the functional form of the primal cost functions that we have in terms of strong convexity, then we can actually have that the set is compact in the dual domain of the set of minimizers is compact. So yeah, we had to actually add this additional assumption in order to get the compactness, but it is not too restrictive from what we have seen in the different setups that we have created numerically.
I see. So essentially, with the strong convexity of the cost functional, you get essentially you have a singleton, right, for the minimization problem.
Yeah.
Then you have the timers.
That's whenever we assume that the primal function is Lipschitz. So because we have Lipschitz continuity in the primal function, we can conclude that in the dual domain, the functions are strongly convex, and then we have a singleton, and thus the set is compact. Whenever that doesn't happen, we have to actually apply this additional assumption in which our level sets are compact for the dual cost function. But it is not too restricted for the different settings that we have created.
But at the end of the day, in any case, you will have a connected, compact set of minimizers, right?
Yeah.
Okay. Nice. Okay, I see now the need of basic conditions.
I guess just to complement that answer, we also use the basic conditions to use the invariance principle and also the reduction principle in the analysis.
Perfect. Okay. I guess more related to the workshop itself, unless there's another question. Abhishek, can I ask another question?
Please go ahead.
So where is the computational kind of cost, not cost of the problem, right? Playing a role in the feedback loop? Is it through the timers that are intermittent, or do you have a model of computing?
Yeah, so
we are not seeing.
Like we assume that the dual oracles are going to take some time in order to compute the information of the gradient. So basically what we'll do is that we have this existence of the switching timer, and we're going to take basically like the max between how long will like the worst case scenario for the dual oracles, how much time will they take in order to converge to the admissible precision, and also the admissible time that we obtain from the robustness properties of the hardware algorithm. So yeah, the hardware limitation of the computational constraint is in assuming that the dual oracles are not giving you information instantaneously, but they take some time. So we're going to just wait for them to finish before we use the information in the global optimization program.
Thank you.
Yeah, I would also add the technical reason for this is that optimal algorithms for distributed optimization, like dual-based methods are optimal for distributed optimization. However, when you move to the dual, the gradients of the dual function might not be readily available as the gradients of the primal one. So you actually need to solve a smaller optimization problem in order to get the gradient of the dual function. And this was the main motivation. When you don't have what is called dual-friendly functions, which is functions for which the dual oracle is explicit, you actually need to solve another optimization problem just to compute the gradient. And this is computationally intensive. So we need to take this into account, that in order to get the oracles are a little bit slower in this model. So it will not be immediate access to the gradients, but you need some time to actually compute it.
Okay, perfect.